Hello. Can everyone hear me? Okay. So first, I'm curious, how many of you are local to Toronto? Awesome. Yeah, I just want to thank all of you personally for bringing the really excellent weather. As he mentioned, I live in Austin, Texas, so I had to dig a pea coat out from the back of my closet. But hey, it still works. So today I'm going to talk about making modern web performance accessible, both in terms of people using the web and people building for the web. My name is Amberley, and I work on the Gatsby team, helping to build out things for the Gatsby ecosystem. If you're not familiar with Gatsby, it's an open source framework that helps developers build super fast websites and web apps. It's basically a compiler for the web. I live in Austin, Texas, and I'm on Twitter, if you're inclined to Twitter. So, at the risk of grossly stating the obvious, the way we build for the web has changed drastically. So I'm going to talk about how it's changed, specifically from the perspective of how delivering content on the web has changed. Then talk about the way that we build has changed, has produced performance challenges. And then talk about some strategies to deal with those challenges that have emerged. And then finally, how we can make it easier for folks, for the average developer, to leverage these techniques. So how building for the web and delivering content on the web has changed. You'll see the things I reference are sort of particular to the way that I started learning to build. So starting with static delivery. I don't know about y'all, but when I started building for the web, it was straight up static HTML, CSS, maybe some JavaScript. I could write it, save it, open it up locally to preview in my browser, drag and drop some files over in an FTP client, and boom, it was online. So that was super cool because hosting is cheap, sometimes even free. It was widely supported. I'm going to gloss straight past browser wars and browser inconsistencies. Thank you, web standards folks. So yes, widely supported for the most part. The number of requests was much more limited. You requested an HTML page and some assets, and then there you go. And file sizes were typically smaller. We weren't serving as much. So delivery was super straightforward. The browser made requests to the server grabbed some ready-to-go HTML, CSS, JavaScript, images, etc., and sent it back. But it also had a lot of limitations. So this is a screenshot of some code from an old portfolio site of mine, and reading the actual code isn't important here. These are two different HTML files for two different portfolio items. You can see at the top, the main nav is completely duplicated, copy-paste between the two files. Same thing for the secondary nav underneath, pretty much copy-paste. And then below that, the markup for the information about each item was pretty much the same, just the content was different. So it was a lot of copy-paste, 100% hard code, and a lot of repetition. Adding something usually meant updating it in a bunch of other places, which is tedious and brittle and error-prone. And overall, static just meant there wasn't much we could do here. It was delivered as is. So we move on to server-side rendering. This little snippet is some PHP. For myself and for so many other people, my introduction to this type of development was building with WordPress. So again, reading this isn't important, but this is a PHP template for displaying a single post on a WordPress site. And the parts I've highlighted here are the get header, get sidebar, get footer. There was more that we could do here, defining things in one particular place and then pulling it over only when it's needed. So this is rad because we can separate our code and our data, or our content. A lot of the content management experience can sort of be lifted out of the code. We can reuse code. Like I mentioned, we can edit the header in one place without having to worry about updating it in every instance of where it's used. And then there's a whole new world of opportunity to use dynamic data because the views are being dynamically generated on the server. So things can update as data changes. So the web starts to become a lot more interactive. So now our delivery looks slightly different. For static resources, it's still pretty much the same story, but requests for dynamic resources are forwarded onto server-side code, which interprets the request, reads out whatever information is required from the database, compiles the data with the templates, and sends it back to the browser to render. So there are some trade-offs here too. There's a higher cost than static hosting, and it's not quite as straightforward. It's complex and resource intensive. With servers and databases, there's operational complexity and downtime risk. With WordPress, for example, it needed to support PHP and MySQL. Maybe even had managed hosting to specialize in optimizing delivering whatever you were working with, which was more expensive generally. And then there's just a lot more vulnerability involved. There's a lot of surface area that can be compromised, and it can take a lot of effort to keep it all secure. So then we go super hard in the other direction, pushing all the work off to the client with client-side rendering. And we start seeing libraries like Angular, Ember, and React, and now we're on a quest for app-like behavior in the browser. So with just client-side rendering, our HTML tends to look more like this. The server delivers it without any content. There's just this root div. And when all the JavaScript is downloaded and everything is parsed and compiled, the browser renders that content into that target div. So again, our delivery cycle looks a little bit different. Again, we're sending static assets, but this time we're relying pretty much on JavaScript to dynamically construct and render the view. And in a lot of ways, this is also awesome. We can build app-like behavior into the browser with no full page reloads required. It's much easier to support rich interactions. We have synthetic events that normalize some of the inconsistencies between browsers. It takes away some of the lift of manipulating the DOM directly. With Node.js and NPM, we see an explosion in the ecosystem, and it becomes easier to leverage the collective work of the community. Again, hosting static files is generally cheaper and simpler. The delivery is simpler. We don't have database lookups or server computation. We're just returning static files. And we still have some of the benefits from before. We have separation of concerns, and we're still repeating ourselves less. But on the downside, we're doubling down on the amount of JavaScript sent to the browser, or tripling down, or quadrupling down. Initial page load can be super slow. More JavaScript to download is more JavaScript to parse, and JavaScript is an extremely expensive resource. We're depending on JavaScript to be enabled. When it's disabled, the user sees nothing. And there are ways around this a little bit with universal JavaScript, because we can run JavaScript on the front end and the back end. We can server-side render first, and then let the browser take over. But there's just a lot to deal with there. There's a lot of tooling behind it, and now we have to think about bundling and transpiling, making it all play nice together, so there's a lot more overhead. So where does that leave us? There's a reason we've ended up here, and it's pretty cool that we have so many tools now to build rich experiences for the web. But it comes at a cost. We're sending huge amounts of JavaScript, and in practice, we're assuming JavaScript support. So when we push more of the responsibility from the server to the client, we become super reliant on the user and the user's device. And often, the user's device doesn't perform at the level that we might hope or expect. So let's talk about how this impacts our users. As previously Harry said, time is valuable. We want users to interact meaningfully with what we build. Otherwise, why bother to put it online? Last year, an article from Google shared that the average time it takes to fully load a mobile landing page had decreased by 7 seconds, but it still took about 15 seconds. And that's in a context where more than half of mobile site visitors will abandon a page load that takes longer than 3 seconds. So slow page load and giant payloads are costly. Access to a high-speed internet connection and unlimited data is not equal. Over half the world is now online, so it's not yet everybody. 2/3 of the world's population now has a mobile device, and of those, over half are smart devices. But among those smart devices, there's a huge disparity in the quality of hardware and the affordability of data. Globally, the average smartphone user uses 2.9 gigs of data monthly, and in North America, that's 7.1. So what that means is that what we build is imbued with bias. The devices and networks we use to develop on and experience the web on tend to be much faster than what the average user is experiencing. Also, access is situational. This ties back to something that you often hear repeated in discussing accessibility, which is that ability or access is not a binary question. It's not a permanent has or has not. It changes day to day or even minute to minute. It's actually a spectrum, and where you or your users fall is constantly in flux. So it's context dependent. One pretty typical example that you might hear is lacking use of an arm. That could range from a permanent condition to a temporary injury to something situational like carrying a child or carrying grocery bags. Relating this back to web performance, depending on the hardware available to you or the connection situation you're working with, you could find yourself anywhere on the connection spectrum at any time. In this way, we can look at web performance as an accessibility question. Even if you generally enjoy use of a high-end device, top connection speeds, and unlimited data, you still benefit from performance tuning. And I appreciated that we already brought up plain Wi-Fi, because I saw this tweet in the last couple of weeks that I thought did a particularly colorful job expressing this, which is if your web app sucks on plain Wi-Fi, it sucks for millions of people in rural America and billions of people in emerging markets. I also always pay for the plain Wi-Fi, so that's the user. What about the developer experience? Earlier, I said how awesome it was that we have so many tools to build rich experiences for the web now. But on the other hand, in front-end world, we have this sort of chaos. We're drinking from the fire hose, or we're attempting to, anyway. Sometimes I wonder if I was starting now instead of 10 plus years ago, where would I start? When I started learning React in particular years ago, it was in a time period where the phrase JavaScript fatigue was everywhere. Setting up an environment just to get up and running and learning was not a small ask. So I'm not going to talk about the E2 framework or not to framework sort of existential crisis question. What I am going to get at here is these tools are enormously popular for good reason. And given the fact that they are, the questions that I'm more interested in are, how do we make what's delivered to the end user as performant and accessible as possible? And how do we improve the development experience when trying to accomplish that? So that brings me here. Given where we are, what strategies can we use to tackle performance challenges in the current landscape of the way a lot of us build? First, route-based code splitting. Serving a single JavaScript bundle for your site or app may sound faster because it limits the number of requests, but it can slow things way down. The larger the bundle, the longer a user has to wait to interact. Once it's all loaded, future interactions will be super speedy, but at the price of a giant upfront download and parsing. So route-based code splitting creates smaller bundles for specific routes and shared bundles for common code. It allows us to fulfill only exactly what the user needs at the time they need it. 2, serve assets with HTTP2, which we've already heard a little bit about. HTTP2 is a major revision of the HTTP network protocol. It leaves the semantics of HTTP intact, but modifies how data is transported between the server and the client to make sort of the request-response cycle more efficient. In HTTP1, this cycle looks something like this. Here, the first request is for our index.html, which gets returned from the server. And when it does, the browser discovers references to things like style sheets, scripts, images, and then it will separately make requests in their own request-response cycle. In HTTP2, this looks something like this. Here again, we have our index.html page that gets requested and sent back from the browser. But this time, as the browser comes across references to other assets, it can go ahead and just shuttle those requests through on the same connection. So we're not spending the time on these different cycles. A step further, HTTP2 enables server push, which lets us actually send site assets to the browser before it even knows it needs them. So here again, we're sending our index.html request, but this time when the server gets the request, it already knows, hey, you're also going to need these things, so I'm just going to push that through for you as well. 3, setup background prefetching. Prefetching uses browser idle time to prefetch resources a user will definitely or likely need in the near future. After it's finished loading the current page, it will start quietly prefetching specified resources. And this can make the perceived load time of the next route feel nearly instantaneous. And there are different ways to do this. One is predictive prefetching. One project doing that is Guess.js. It uses analytics and machine learning to enable prefetching based on the user's likely behavior. Another is to observe the user's interaction with the page and react accordingly. Chrome's Quick Link project detects links within the viewport, and if the browser is idle and the user is on a sufficient connection, it will prompt prefetching. 4, use a service worker. A service worker is a web worker that runs in the browser separately from the main thread. It essentially allows your site to act as its own network proxy. For example, if you're loading a route that requires an image, the service worker can intercept that request, and if it already has that image cached, it can go ahead and hand that back to you instead of making a new request. If it doesn't have it, it can shuttle that request through, receive it back, give it back to you, but also cache it. So the key part there is that it caches it. So if you need to make that request again, you can forego that duplicative request. Doing this can speed up the loading of pages pretty considerably. It actually also allows us to craft an offline experience in the browser. And service workers do a lot of other things, but that's sort of the scope of what I'm going to mention here. 5, lazy load non-critical assets. Lazy loading is a technique that puts off loading of non-critical assets at page load time, deferring them to when the user actually needs them. A go-to example of this is, say we have an image gallery, a large image gallery on a page. If we don't have lazy loading enabled, the user navigates to that page and they don't scroll down, they've incurred a significant download cost for images that they're never going to look at. If we do have it set up and they don't scroll down, they don't have to incur that wasteful cost. If they do scroll down, then we can load it in on demand. So by deferring that load until the user actually needs it, with an offset probably, we minimize the waste. For those of you who might be familiar with the purple pattern, this is probably adding up to all sound pretty familiar. The purple pattern was coined by the Google Polymer team and is essentially a methodology for building web apps that load quickly and reliably. You push the minimal code needed to get interactive and render the initial route, and then use a service worker for caching and pre-caching resources, and then lazy load remaining routes on demand. So further, 6, only ship live code. If the user's never going to need it, why send it to them? With tree shaking, you can identify code that's not being used so that you can go ahead and get rid of it. The term tree shaking comes from thinking of your application and its dependencies like a tree. Each node in the tree represents a dependency for a distinct functionality for your app. As your app matures or as your tree grows, you may still be pulling in dependencies that you were using at one time but aren't anymore. Or you may be pulling in a whole library but actually only importing and using one tiny part of it. So the result is unnecessarily shipping code that will never get run, which is not ideal. 7, serve static files as much as possible. With this approach, you can build static or server render your pages during build time to generate HTML to be served for every page that the user can access ahead of time. There are huge benefits to this. You can serve requests super fast because you don't have to spend the time rendering on the server when it's requested. Site visitors generally experience faster load times loading from a global CDN because it doesn't have as far to travel if it's cached close to where the user is requesting it. And it's more stable because you don't have to worry about scaling up servers and databases. By doing the work at build time rather than runtime, you can leverage the benefits of both serving static assets and a full-blown web app. You don't have to sacrifice the benefits of one approach to reap the benefits of the other. So, okay, this sounds great. How do I do it? Comprehensive checklists clock in at 50 plus things to consider. This one from Smashing Magazine at the beginning of the year hit 63. These checklists exist, but they can be costly and time-consuming for teams to implement. There are people who've built their entire careers on performance engineering, as we've heard from today. There's a lot of specialization and a lot of effort that needs to go into that. And it's really hard to get right. While I was working on this, I happened to come across a talk from Gatsby co-founder Kyle Matthews from really, really long ago, like 2 years ago. The same performance checklist from Smashing Mag in 2017 had 33 items. So the lift is getting progressively heavier. Also, I'm going to stretch the car metaphor even further from what you've heard already today. I relate this to driving a high-performance car. Do I need to understand the inner workings and build process of a high-performance car, like to an implementation level depth, in order to drive it? No, I don't. I just need to know how to drive the car. Is it possible to learn every tiny detail to build out a perfectly tuned vehicle yourself? Yeah, but most people don't. So also, I don't know fancy cars. I searched this on Unsplash, so this is what you get. If you're a car nerd and it's not fancy, I'm sorry. Funny enough, I happened across this tweet in the last couple weeks from Kent C. Dodds to much the same effect. Understanding how your abstractions work will enable you to use them more effectively. This isn't to say that you have to understand everything about your abstractions to use them at all. For example, I know very little about how my car works, but I can still use it as effectively as I need to most of the time. So we have these strategies, but they can be a huge lift. How do we make it easier for folks to implement? We can use tools to get most of the way there automatically under the hood. More car metaphors. We can solve a lot of these problems at the framework level. Make it easy to make it great out of the box by default. This is one of the foundational ideas behind Gatsby, making performance a baked-in first-class concern. And not just Gatsby, but so many other great tools trying to solve this problem in various ways. Then use auditing tools. There's so many awesome auditing tools out there now that make auditing performance super approachable. There's PageSpeed Insights, Mobile-Friendly Test, Web Page Test, Lighthouse. There are tons of tools out there. So they help us identify areas of opportunity based on your actual implementation, what you're actually building. So between these two steps, first we've laid a strong baseline foundation and baked in a strong performance strategy from the start, and you can find tools that align with the performance strategy that you want to take. And then we've identified other areas of opportunity based on what you've created. So then, if you want, or if your business requirements dictate, dig in, specialize, go all out on that Smashing Mag checklist and everything else. But if you don't, you should still have a strong and performant baseline. At Gatsby, we talk a lot about the idea of progressive disclosure of complexity, sort of the idea of introducing complexity gradually so as not to overwhelm. So that's kind of what I'm getting at here. Make it easy to make our baseline great, and then opt in to scale it from there. So now I'm going to put on my Gatsby hat a little bit and relate these techniques that I've talked about to the way we're trying to make this out of the box for developers. Once again, there are a lot of great projects out there that have their own methods and opinions for this, but this is how Gatsby uses these techniques. Implement route-based code splitting. Yep, by default. We use Webpack for this, so you don't have to be a Webpack master to take advantage of these optimizations and roll your own Webpack tuning. I'll go through a quick simplified example of what this looks like in a built Gatsby project. If we go through this, these top-level directories, the 404, about, contact, etc., they represent different routes and contain their respective precompiled HTML server rendered at build time. This app-unique hash nonsense is our comments chunk, and it's going to contain vendor dependencies that all of our routes depend on. Then we have these components, component triple dash, which also represent all of our routes, but they're JavaScript representations. So these are the files that will take over after we've done the initial static load of the first route, and client-side rendering takes over. Because after Gatsby's first static load, it just boots up a React runtime. So it's just a React app. And then we have this 9-unique hash file over here, which represents some split out dependencies for a different route, probably. Maybe on the contact page, we're using formic for forms or something like that. So with route-based code splitting, we can only incur the cost of shared dependencies and route-specific dependencies once. So if we have a particularly heavy route, it won't drag down the performance of our entire site or application. HTTP2 is a bit trickier. It can be super hard to implement, and it varies by host and your server setup. So this is, in Gatsby, this is where we can make really excellent use of the plugin ecosystem. As an example, Netlify is an awesome static site host used by tons of folks, and we love it in the Gatsby community. If you're using Netlify to manage deploying a static site or a Gatsby site, you can use the Gatsby Netlify plugin to take advantage of HTTP2 and server push critical Gatsby scripts by default. Set up background prefetching. Yep, so Gatsby has a link component for linking internally that enables prefetching. There are sort of two pieces to the way this works in Gatsby. First, we use the intersection observer API. The intersection observer API is a browser API that's used to perform some action when an element enters or leaves the viewport. This is an incredibly adorable example created by my coworker Dustin to visualize the intersection observer API. You can see as I scroll up and down the page, the emoji changed. There's an offset to it, but the emoji changed from visible eyes to not visible hiding face emoji. So relating this back to Gatsby, on load, if a link is in the viewport or above the fold, colloquially, prefetching will be triggered for assets associated with those different routes. If a link enters the viewport on scroll, prefetching will be triggered for those assets as well. These requests are heavily deprioritized and will only fire when the browser is idle. So it's kind of a polite hint to the browser, hey, you're probably going to need this. However, when a user actively hovers over a link, which is a strong indication that they'll actually navigate to that link, we'll actually fetch these resources at a higher priority. So here I'm on the Gatsby homepage, and as I hover over nav items, you can see requests automatically cycling through in the network tab. So by the time I actually click, resources are fully loaded, so routing feels super snappy. But what if we're on a slow connection and the user doesn't want to download things that they're not necessarily going to need? We got this great PR from Adi Osmani, sort of Google performance wizard, to limit this behavior on really slow connections and to respect if the user has indicated that they want to save data. So now, lazy load non-critical assets. A great example of this in Gatsby is the Gatsby image component. The Gatsby image component is designed to work with Gatsby's data layer to optimize images and image loading on Gatsby sites. This is the demo site for Gatsby image. As you scroll, an intersection observer fires and actually loads needed images in place. So also, Gatsby image optimizes images by default at build time. Optimizing images is low-hanging fruit for performance and should be automated. So with Gatsby image, you not only get image optimization for free, you're not even serving optimized images if the user doesn't need them. Just another representation of this. On the left is the demo site, and the right is the network tab. And as I scroll, you can see the different requests rolling in for the different images. Use a service worker. For adding a service worker, again, we turn to Gatsby plugins. The offline plugin adds drop-in support for making a Gatsby site work offline and more resistant to low-quality network connections. It creates a service worker and loads it in the client for us. So this plugin works best with the manifest plugin, and together they get you most of the way toward fulfilling the very baseline requirements for a progressive web app, which we're going to hear more about later this afternoon from Hassan. Only ship live code. Yep, by default. In Gatsby, we use Webpack and Terser.js for this. Terser is a JavaScript optimization library. Webpack marks unused code during bundling, and Terser eliminates it during the minification process. So again, you don't have to understand the intricacies of Webpack or Terser or any other tool to get the baseline benefits of it or to drive the car. When you think static assets, it may be reasonable to think, but I want my site to be dynamic. I can't have a static site. But static assets don't mean a static app. I said this before, but Gatsby server-side renders at build time, producing static HTML. When a user hits a Gatsby site, they're served that pre-rendered static HTML first. After the initial static load, the site is rehydrated into a full React app. So you get the fast subsequent page loads of a single-page app on top of the fast initial static render. As an example, this is the Gatsby Swag store. At build time, we pull in Shopify product information and data and pull in images from Shopify and optimize them. So we build as much as we can static, because why do at runtime what you can do at build time? And then on the client side, we use Auth0 to do user management and the Shopify Buy SDK to manage the cart. So it's an example of a fully functional e-commerce site leveraging the best of static and dynamic. So personally, my favorite part of all of this is that it enables everyone, but especially early career devs, to get started productively super quickly and with a performant baseline. It handles the stuff a lot of people don't want to do so they can just get started creating. People need to get started somewhere, and we want their baseline to be great when they do it. So now I'm going to talk a little bit about a demo that I built to show some of this. And first of all, yes, I made it about my dog. He's the best pupper. His name is Riggins. The homepage has a little image gallery on the bottom, and there are a couple routes for emergency information and commands that he knows and stuff like that. So I made this site for him, and I started off building it entirely static, plain HTML and CSS. And then I created the Gatsby version by scaffolding out the Gatsby default starter and pretty much just porting over the static HTML and CSS markup and styling. So checking out the Elements tab of both sites, the markup, like the core markup of it, stays intact. I also don't have to repeat myself as much. On the left is the static markup for the gallery on the home page, and on the right is the gallery component that I made. So we're just mapping over the images we want to show instead of duplicating the markup. In the static site, I'm fully reloading HTML pages on click. This is showing the Gatsby site where you can see, as we discussed before, I'm prefetching resources for the route that I'm hovering over. So when I actually click and navigate, it feels pretty instant. I've also used the exact same image files in between both sites. In the static site, the images are served unoptimized. And actually, the image gallery ones, I cheated a little bit because I used Gatsby to pull the images and then pulled them over. But in particular, you can see this feature image, which I just got directly off my phone, is a blocker. In the Gatsby site, Gatsby optimizes all of the images for me at build time, So the exact same image input between the original site and the Gatsby site looks like this when it's downloaded on the Gatsby site instead, without me doing anything to manually tune the image. In the original site, all of the images on the home page load when I load the page. And because it takes some time for the feature image to load, you get this kind of janky resizing div jump behavior. In the Gatsby site, the images load in place, so there's no reflow jump. So it looks less janky. In the Gatsby site, just by using the Gatsby image component, we also get this automatic lazy loading behavior. So you can see as I scroll, these images load in on demand, rather than all loading in on initially hitting the page. I ran Chrome Lighthouse audits for both sites. Both run at the same time, both in incognito mode, and both sites are hosted on Netlify. So this is the Lighthouse score for the static site. Has a score of 51 for the performance. It suffers a lot, particularly for that giant feature image, but looking pretty good on accessibility and best practices. This is the audit result for the Gatsby site, and just to reiterate again, it's pretty much the same markup, the exact same image files. I just pulled over the CSS style sheet. So the user isn't sacrificing anything. We still have great scores in accessibility and best practices. And really, the user is getting a more optimized experience than in just serving the static site. So the takeaway here that I want to communicate is we don't always have to re-engineer optimizations for good default performance. We should be making it as frictionless as possible for web builders to create great experiences for users of the web. So I'm interested to see all the ways that we as a community continue to make it easier for people to build well. And thank you all for having me for my first time in Toronto. Again, you can find me on Twitter, and you can check out the slides. I have them online here. So thank you all very much.